Hi guys, welcome back to the channel. In this lecture, we are going to discuss about one problem on continuous beam in which we need to find the load factor, right? And we will be solving this problem using static equilibrium method. Okay, so basically in this problem, this is a continuous problem having two span. Okay, so in this the plastic moment capacity of this beam is given 30 kilonewton meter, right? And we need to calculate the load factor. Indirectly, we need to calculate what is the collapse load for this beam, right? So basically, load factor we have already discussed in the last lecture. Load factor is collapse load over my working load. So in this problem, the working loads are basically 20 kilonewton and 10 kilonewton. Okay, so we need to find the load factor basically. Okay, so lambda, we will take lambda as a load factor. So this will be collapse load upon my working load. Okay. As you can see that this beam is statically indeterminate, and static indeterminacy of this beam is one reaction is from here, one reaction at this B point and one vertical reaction at this C point. I am neglecting the horizontal reactions. So total number of reactions are 3, equilibrium equation are 2. So static indeterminacy of this beam is basically 1, right? And number of the plastic hinges, required for collapse are basically 1 plus 1. Okay, this will be equals to 2, right? So we know that the number of the plastic hinges required are 2. Okay, now let us see where is the possibility of the plastic hinges. Okay, where the plastic hinges will form. Plastic hinge can form at this point, okay, at this point and at this point, because at these point there will be a peak moments at these point. Okay, let us denote this point by E, D and E. Okay, so there are chances of plastic hinge at point D, B and E. Why? Because there will be moment peak. Peak moments will be there. Moment peaks. Okay. So if you draw the bending moment diagram of this thing, the bending moment diagram will be maximum at the peak bending moment. The peak of the bending moment diagram will come under this point load, at this support and at this E point, right? So this is done. Now you can see that the static indeterminacy of this beam is 1. So we need to take some redundant over here. Okay, this thing we have already discussed in the last lecture. So we need to calculate the load factor. So what I am doing over here is I am multiplying this working load by lambda. Okay, so this is lambda, 10 lambda kilonewton. This is 20 lambda kilonewton. Okay. Now I am taking MB as redundant. MB as redundant. Okay. Why we are taking moment as a redundant? Because we need to write equilibrium equation in terms of moment. Okay. So I am assuming that. So if you take MB as a redundant, there will be internal hinge at this point. Okay. Internal hinge at this point. So this beam, we can divide this beam into two parts. At this point, there is an internal hinge because we are considering MB as redundant. Okay, so moment at this point will be 0. Right? Plus, when you are taking MB as a redundant, the second part, the second beam will look like this, and bending moment I am taking, the redundant I am taking like this. Okay, this is basically MB. Okay, and these two values will be equal. Here this point load is acting 20 lambda. We need to find the load factor. That's why we multiplied load into load factor, and this is 10 lambda, right? Now let me draw this figure a little below. This will be, because we need to draw bending moment diagram also, we need some space between these two diagrams, right? So the bending moment will act like this, will act here, it will act like this. This is MB, this is MB, this is MB. Okay, so you can see that if you draw the bending moment diagram, we just divide this beam into two parts and we'll superimpose the results. Okay, so if you draw the bending moment diagram for the first part, it will look like this. At this point, the bending moment will be 0 because there is an internal hinge over here. Okay, this beam is stable. Okay, so because there is one support at this point, there is support at this point. This is internal rollers. This is roller support at this point. Okay, so this beam is stable basically. So this value will be the value of this moment will be, bending moment will be PL by 4. Okay, so P is our 20 lambda, L is 6 divided by 4. So this value will be 30 lambda. 30 lambda. This moment, maximum moment value is 30 lambda. At this point, the maximum value is 10 lambda into 6 divided by 6. Sorry, 6 divided by 4. So this will be 3, 2, 5. This is 15 lambda, the maximum value of the moment. Okay. Now if you draw the bending moment diagram for this figure, this bending moment diagram to balance this moment, there will be the reaction force, the couple will act like this. Okay, to balance this moment. So the bending moment diagram will somewhat look like this. Okay, so at this point the bending moment is MB and this is negative because this is a hogging bending moment, right? This direction is positive, this direction is negative, right? So basically this is the hogging bending moment. Now what we will do? Now we will be writing the equilibrium equation in terms of moment. Okay. So first I'm considering that this is A, this is B, this is C. I'm considering that AB span will fail. Okay. In the case of the continuous beam, we have to check individual span. Okay. So first I'm assuming that AB span will fail. AB span collapse. Okay, so if AB span collapse, the plastic hinge will form at D and B. So plastic hinge will form at D and B. Okay. So when this AB portion collapse, it will look like this. This is D point, this is B point, this is A point. Okay, this is during collapse. This movement is during collapse, right? So when this thing happens, we will be writing the moment equilibrium equation, static equilibrium equation of moment at this D point. Okay, so if you write the static equilibrium equation at D point, so MD equals to 30 lambda minus of, this will be MB by 2 by linear interpolation. We have already discussed this thing in last lecture. This will be MB by 2. Okay, so if the plastic hinges are formed at D and B, MD will be equals to MP and MB will be equals to MP. Okay, right? So you can see that MD direction, the direction of the M, this is the direction of the rotation. Okay, so direction of the MB will always be opposite to direction of the rotation. So this is MP, and this is MP. So MD will be equals to MP, right? So and this is 30 lambda minus of MP by 2. So this equation will be mp plus mp by 2 equals to 30 lambda. So 3 mp by 2 equals to 30 lambda. Here you can see that mp value is given 30 kilonewton meter. Okay, mp value is 30 kilonewton meter. So I can write 3 into 30 over my 2 divided by 30 equals to lambda. So lambda comes out to be 1.5. Okay, so the value of the lambda is 1.5 when plastic hinges are formed at A, at D, D and B. Okay, right? So this is the first case when we have assumed that our span AB is collapsing. Okay, now we'll see what will be our load factor when this BC span will collapse. Okay, and remember, in continuous beam we need to check the individual spans, right? Now I'm saying that BC span will collapse. BC span will collapse. Okay, so when the BC span is collapsing, the plastic hinge will form at B and E point. Okay, the plastic hinge will form at this B point, B and E. Okay, so the plastic hinge will form at B and E. There is no plastic hinge at D. Okay, the plastic hinges are forming at B and E point, right? So at this point there is no plastic hinge. Okay, when we are assuming that collapse is taking place, collapse is happening on BC span, then it will deflect like this. Okay, right? So when the collapse is happening on BC span, the plastic hinge will form at B and E. So I will be writing the static equilibrium equation for the E point. Okay, so ME will be equals to 15 lambda minus of, again through linear interpolation, this will be MB by 2, this will be MB by 2, right? This will be MB by 2, and again you can see that the direction of the MP will be like this, opposite to the rotation. MP will be like this. Here MP will, again MP will be like this. Okay, so ME is basically MP. This is equals to 15 lambda minus MB by 2. MB is equals to again MP, right? We have already, this moment is basically negative, but we have already taken MB as negative, so no need to keep MP minus MP. Okay, so we have already taken this direction. So this is MP by 2. So this, if you solve this thing, this is 3 MP by 2 equals to 15 lambda. Okay, so again 3 into 30 divided by 2 into 15 equals to lambda. So 15 to 2. So here lambda comes out to be 3. Okay, so when the lambda is equals to 3, when plastic hinges are formed at B and E point. Okay, now again the third case. Now I am saying that the plastic hinges are, let us suppose this is basically the partial collapse of the structure. This is basically the partial collapse. This is partial collapse. Okay, why partial collapse? Because only one structure is failing, only one part of the structure is failing, but it is a collapse. Okay, this is partial collapse, right? So let us assume that this span is also the collapse mechanism is forming in both the spans. Okay, in both the spans. So for that, the plastic hinge should form at D point and E point. Okay, so now I am assuming that the plastic hinges are formed at this point and this point, because peak moment will be there, right? Plastic hinge can form at this point, or this point. So first I have assumed that the plastic hinges are formed at these 2 points. Then I assume that the plastic hinges are formed at these 2 points. Now I am assuming that the plastic hinges are formed at D point and E point, right? Now this is a very important case. So I will be writing again equilibrium equations for this D and E point. Okay, Now when the plastic hinges if the plastic hinges are formed at these 2 points, okay, so the deflection during the collapse will be like this. This is during collapse. Okay, for the collapse, the deflection will be a straight line. Okay, now you can see that here the direction of the movement will be MP like this. Okay, direction of rotation is like this, so MP will be opposite to this rotation direction. Here you can see that again the moment will be like this, opposite to rotation. Okay, now this is the important, now there will be, you will see some important thing over here. Okay, so now let us write the equilibrium equation for the D point. So equilibrium equation for D point. If you write the equilibrium equation for the D point, it will be MD equals to 30 lambda minus of MB by 2. Okay, let us suppose this is our equation first, right? So if the plastic hinge is formed at MD, so this will be MP equals to 30 lambda minus of MB by 2. MB is unknown over here. MB is unknown over here. Previously, we are assuming that the plastic hinge is formed at B point. At that, in that case, the MB value is known to us. But here, MB value is unknown. Okay, because the plastic hinges are formed at D point and E point, right? So if this is the case, this is, let us suppose this is equation 1. Okay, now for this span, for this portion, if you write the equilibrium equation between for the E point, so static equilibrium equation for E point, this will be ME equals to 15 lambda minus of MB by 2. Okay, but remember over here, remember ME will be minus of MP. Why minus of MP? Because here you can see that this MP is creating basically the hogging moment. Okay, that's why we need to keep here minus MP value. Okay, so this is our equation 2. So this is the important part. This direction of the MP is very, very important. Okay, and you will always take MP opposite to the direction of the rotation. Here the direction of the rotation is like this. Here the direction of rotation is like this. So MP is opposite to this rotation. Okay, and you need to check the sign of the MP, right? Because here this is positive at this D point and at E point it is negative. Why negative? Because there is that MP is creating hogging moment over there. Okay, so if you solve these two equations, so we have two equations over here. First equation is MP equals to 30 lambda minus of MB by 2. Right, this is our first equation. Second equation is minus MP equals to 15 lambda minus of MB by 2. Okay, so if you subtract 1 and 2, if you subtract 2 from 1, okay, so this value will be 2 MP. Okay, 2 MP equals to 15 lambda, right? These two terms will cancel out each other if you subtract them. So 2 MP, 2 into MP is what? 30. This is 15 lambda. So lambda comes out to be 4. Okay. So when the plastic hinges, is forming at D and E, the load factor comes out to be 4. Okay. Now you can say by the which is a critical one. Minimum load factor is required. Okay, so lambda will be minimum. So lambda will be 1.5 is our solution. Okay. Okay, you need to provide the minimum value out of these three, right? Because the minimum value will result in collapse. Okay. So this is the case. So if you draw the, what you can say that, so the collapse load at this point will be, at this point 20 into 1.5, this will be 30 kilonewton. And this point, this is 15 kilonewton. Okay. So, guys, now we'll see whether corresponding to this load factor, our yield condition is satisfied or not. Okay, we'll see through the bending moment diagram. Now our beam will look like this. Loading system, this load will be 30 kilonewton. This is 15 kilonewton. This is during collapse. Okay, these are our collapse load, right? So at this point, we are assuming that the plastic hinges are forming. So there is a partial, this collapse will be at this AB span. Okay, collapse will take place in AB span. Okay, so here the deflection will somewhat look like this. So if you draw the bending moment, the moment MP moment will act like this. Here the MP will act like this. Okay. So now, if you draw the bending moment diagram for this case, so it will look like this. Here this is MP. Okay, so this value is MP. This value again is MP. Now for this part, let us check for this part. Okay, you calculate the RC reaction, RC into 6, this is 3, this is 3, minus 15 into 3 plus 30 equals to 0. If you take moment equilibrium about, if moment summation MB equals to 0, right? So if you solve this thing, RC comes out to be RC into 6 equals to minus 45 plus 30. So RC is equals to 15 by 6, right? This vertical reaction is 15 by 6. Okay. So 15 by 6 into 3. If you multiply 15 by 6 into 3, so at this point, the bending moment is 7.5. Okay. And again, it will go like this, right? So this is the bending moment at collapse. This is the bending moment at collapse. Okay, at this A point, the bending moment is 0, simply supported end. This is also a simply supported end, so bending moment is 0 over here. Okay, so you can see that this is the bending moment at collapse. The plastic hinges will form at this point and at this point, right? So this is the case. If you check this bending moment diagram through these two cases, it will not satisfy the yield condition. Okay, so this diagram, M is always less than equals to MP. So yield condition is satisfied. Okay guys, so this is a very, very good problem in which we saw what is the importance of the direction of this MP moment, right? So guys, if you have any doubt regarding this, you can write in the comment section. Okay, so thank you very much.